So now I want to just present quickly the math module. So I don't think you really need help here. The math module just includes all kinds of mathematical constants and mathematical functions, the very classical ones basically. So let's import the math module and then print the two main constants it defines, math.py and math.e. So you see here the values. And you see that you can access all kinds of trigonometric functions, and for instance math.tan of some fraction of pi, and you can compare this with sine over cosine and you will get true. You can do degree and radian conversions, so it's simply like that. You can take arc cosines and arc sines, and you will see that here there is some numerical error that is introduced by the floating point arithmetic. So this is why it's false. The difference is actually very, very tiny. So if I do plus, I should get something very tiny, and you see it. I can compute square roots. I can compute floors and ceilings as well. So you see all the different ways here you can do things. You can also do exponentials and logarithms. So I have here some different tests I can do. So compute the logarithm in a certain base. Logarithm of 32 in base 2, I get 5. 10,000 in base 10, the log of 10, the natural log, of course. I can compute the number of digits by hand by using this composition of the log and the floor. And finally, I can take an exponential by just mat.x of 5, or I could just take mat.e exponent 5, but you'll see that here it says false because there are some numerical errors that are being done, particularly on the right. It's only an approximation of the right answer, and the one on the left will be more accurate. Okay, so other things you can do, you can use factorial, and you can see here the factorial of 100. You know, it's a very long number, and in bits it's going to be 525 bits long. You can not use factorial for a float, and that gives you a value error. So this is the output I would ask to be printed. So I can also ask for the internal representation of a number, and this is given by frexp. So if I take 1.1 float, it will tell me that it's 0.55 a float times 2 to the 1, or for e it will be 0.6795 etc. times 2 to the 2, so times 4. So the precision here is lower than the 2 to the 53 precision. The precision of this number here is 2 to the minus 53, and this is used to adjust the magnitude of the number on the left. And the number of the left is always a float between 0.5 and 1.